In section 8.3, we're going to look at what it means to take a derivative of a function of two variables. This is our first attempt at using calculus to analyze these functions. And it's important to know that we're not going to introduce a new kind of derivative. There's nothing new we're going to be doing necessarily. It's just about how do we take a function of two variables and think about it as a function of one variable. And then at that point, our derivative rules are all going to be the same from what we learned in the Calculus 1 course. And this is similar to what we've done in the last two sections. Our priority is to look at a cross-section of the function, and that is setting one of the other variables equal to a constant. And then when we have that, we will look at the derivative of that one-dimensional function. So to start, let's look at our example from 8.1. A store sells both xylophones and yo-yos, X being the number of xylophones, Y being the number of yo-yos, and we look at the profit gained from that function. So we have a table of values that gives us the different function values. Looked at this for a few sections now. And we found in section 8.1 that the profit can be written algebraically as P of xy equals 10x plus 4y. Now we've looked at cross sections before, but now we're going to do so with the intent of finding the derivative of those cross sections. So first let's look at px0. That is where we're fixing y to be 0, and then we're just looking at the number of xylophones sold. So we're going to highlight this in the table where we're talking about. These are all the values where where y is 0, and we're going to look at the profit there. We found before what this function actually is. This is p of x is equal to 10x. And we know we can find this out by saying that every time we add, so for every 10 xylophones sold, the profit increases by 100. And this is the idea of a slope, or an f of b minus f of a over b minus a, the secant line, the slope of the secant line. We can get something like 100 minus 0 over 10 minus 0 would give us 10. And that is the derivative of that function. Also, what we're going to be doing in the next section as well is if we have this function here, p of x equals 10x, we know the derivative of that function. We should write this as p of x 0 still, is just going to be 10. It's the slope of that line. All right, when we look at a different cross section, we're going to get a different derivative. So let's do that again. So here we're going to look at p of 0y. This is looking at a derivative in the opposite direction. This time we're setting x equal to 0, and we're thinking about what happens when y increases. And again, we found that this function is equal to 4y. For every 4 yo-yos sold, the profit increases by 40. So we do a similar kind of calculation, 40 minus 0, 4 minus 0. I should say not every time 4 yo-yos sold, every time 10 yo-yos are sold, increases by 40. So here we go, and there's our 4, which is the slope of our line for y. So again, what we're doing is we're looking at a cross section, which is a function of one variable, and then we are taking the derivative of that function in our normal kind of way. In this case, we get a 4. Let's do this one last time with just a different cross section. This time we're thinking about a different kind of cross section when y is 20. This is a cross section in the x direction, so a horizontal cross section there. We found similarly that this is going to be the formula. In fact, we won't even use the formula this time, but we'll say it later. But how can we find the derivative just with this information? What we could do is we could look at one part of this. So let's look at just these two numbers right here. And we could do a little formula again, f of b minus f of a over b minus a. That's a way to estimate what the derivative is going to be. In this case, it's going to be 180 minus 80 over 10 minus 0 if we're looking at the corresponding x values there, which would give us a 100 over 10, and we get another value of 10. And we showed in the previous video that this function has the same slope always. It doesn't change anything. The formula here is going to be 10x plus 80 to get that function. Another way of doing this is we know that p of xy is 10x plus 4y. So p of x20 is going to be 10x plus 4 times 20. There is our 10x plus 80. That is a function of one variable, and we're taking the derivative of that function as we're used to taking them. So again, we're not doing a new kind of derivative. There's no new thing that we're going to be doing. It's just about how do we look at this function of two variables and think about it as a function of one variable in different directions. This is what we're going to be talking about as a partial derivative. So let's define this term. And to do this, let's first look at the definition of the derivative in general. So the limit definition of the derivative, f prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h is our limit definition. And this is basically the idea of doing f of b minus f of a over b minus a. We could think about this as the limit as b approaches the value of a. We're letting those numbers get closer and closer together, and we use a limit to do that. This is our limit definition. And our definition of the partial derivatives are going to be very similar to that with one tiny detail. So it's important to note that we are going to have two different derivatives when we're talking about functions of two variables. That is the derivative with respect to one variable and a derivative with respect to the other. And this is why we call these partial derivatives. It's not giving us the whole picture, just a part of the picture. So the partial derivative of f of xy with respect to x, we're going to use this notation f subscript x xy is going to be the same limit definition, except that our function values have two inputs, x and y, but the y part of it is just going to be left the same throughout the whole function, as we're not thinking about what happens to y with the partial derivative with respect to x. Similarly, when we do the partial derivative with respect to y, we're going to leave these x's constant, and we're going to think about the derivative in a similar way as the original derivative. F of x plus h minus f of x, we can see that f of x plus h minus f of x right there. Similarly, f of y plus h minus f of y right there over h. Some notation we're going to use, sometimes we're going to think about the z value as being the function value f of xy. This is very similar to saying y is equal to f of x. And we said if we have the subscript x or y, that's going to give us which partial we're thinking about. And then the other big notation here is this sign, this partial derivative notation. So this is very similar to dx of something. But this time we're going to be using this partial notation, which looks like a kind of weird 2 or a weird d. And it just tells us that we're not doing a normal derivative, we're doing a partial derivative. And then sometimes you can write this as dy or dy dx, and this time we're going to say dz dx, because that's what our function is as a whole. Okay, so this partial notation is very similar to the ddx notation we had before, but it gives us the added information that we are doing something in a function of two variables. We could also evaluate a function at a point. So the partial derivative is a function. We could plug in two numbers a, b into it. And to do this with the partial notation, we could write a vertical bar, evaluate at a, b. This is very similar to saying that f prime of a is the same thing as d or dy dx evaluated at a. We don't use that notation a whole bunch, but it is there for us to use. So let's look at some examples thinking about derivatives in functions of two variables. And note that we've already thought about this in a few examples. When we think about is the function increasing or decreasing, that is really thinking about the sign of the derivative of these functions. So here's our example. Consider the function capital T of TA. So capital T is going to be the current temperature in degrees Celsius. Little t represents the time of day in hours since midnight. And A is the altitude in meters. So the idea here is that at different times of the day, the temperature can be different depending on where we're at. And then it also matters how high off the ground we are, the temperature can be different. So this might be if we're stuck in like one location, and thinking about if we can go up and down in some way, the temperature is going to change. As we go up, the temperature is going to decrease, right? And as the day changes, it's going to increase, decrease, depending on what time it is. So let's talk about what these things mean in order of words. So explain what capital T of 10, 1000 equals 20 degrees represents. So little t equals 10 says that at 10 hours since midnight, so at 10 a.m., at 10 a.m. and at an altitude of 1,000 meters, the temperature is 20 degrees Celsius. That has nothing to do with derivatives, but it's kind of a review of what we've done in the previous sections. Now let's think about the partial derivative. So capital T with respect to little t, 10, 1,000, what is that going to represent? That is going to be the change in little t, right, at that point. That's what we're looking at. The other one's going to be the change in A at that point. So we're saying at 10 a.m. and an altitude of 1,000 meters, this value is going to tell us how much the time is changing. So it might be easier to say this, let's just say this is equal to positive 1. So what this says is at 10 a.m. at an altitude of 1,000 meter, if 1 hour passes, the temperature will increase by 1 degree Celsius. That 1 right there is equal to the 1 right there. Right, this is saying that if we look at one change in a unit of T, 1 hour passes is plus 1 unit of T, should give us a change of 1 degree Celsius. Now let's think about this in the other way. Maybe we could say this value is a negative 2, and we're saying at 10 a.m. and at an altitude of 1,000 meters, if 1 meter, so we should say, if we go up 1 meter, the temperature decreases by 2 degrees, which is an awful lot. Let's maybe think about it as 0.2 degrees, which is still a whole lot. 0.2 degrees Celsius. Again, that 0.2 is coming from the 0.2 right there. And we're saying if we go up 1 meter, that is plus 1 unit of A. And what happens to the corresponding value of capital T if we increase 1 unit? So in previous sections, we said that for 2, when we're thinking about capital T of T, it's a positive thing. This is increasing with respect to little t, and it is decreasing with respect to A. It doesn't make sense to think about, is this function increasing, decreasing in general? We don't really know what that would mean, but again, if we think about one variable specifically in either direction, we can say something about the derivative. In the next video, we're going to look at a bunch of practice problems thinking about how to calculate these partial derivatives in more detail.